In this lesson, we're going to cover Unit 7, Acquisition 1, Characteristics of Solutions. So some of this should be familiar from first semester, but we're going to go through all of the terms that you're going to need to know, again, as a review. So Unit 7 is all about solutions. So first, let's talk about what a solution is. A solution is formed when one substance disperses uniformly throughout another. Think if you've ever made anything, any like drink with a powder, like a powdered lemonade or a Kool-Aid. Once you put that solid Kool-Aid into the water and you stir and it dissolves, it is dispersed uniformly. You can't see the separation between the water and the powder. It is completely mixed. That is a solution. The solute. These are the dissolved particles in a solution. So if we're making Kool-Aid, the Kool-Aid powder is the solute. It's what is being dissolved. The solvent is the dissolving medium. So the Kool-Aid is being dissolved in water. The Kool-Aid powder is the solute. The water is the solvent. It's what the Kool-Aid is being dissolved in. In Unit 7, we're going to talk a lot about concentration. Concentration is the measure of the amount of solute in a given amount of solution. So let's say I had like a liter of solution. The concentration would tell me how much solute do I have per that 1 liter of solution. The more solute you have, the more concentrated that solution would be. So we keep talking about like solubility. We've talked about solubility rules back in first semester. Solubility is just the ability to dissolve. Ability of a given substance to dissolve. When it comes to solubility, the stronger the attractions, between solute and solvent molecules, the greater the solubility. Last up for definitions before we start looking at some examples. New term, miscible. So miscible is a term that we are going to use specific to solutions. When we're saying that two things are miscible, they are liquids that mix in all proportions. Liquids that mix in all proportions are considered miscible. And the reason why has to do with like dissolves like. So two polar liquids are miscible. They're both polar. Two nonpolar liquids are miscible. Again, like dissolves like. Let's say you had one polar and one nonpolar, like oil and water. We would call that immiscible. So let's look at an example from the lab. So here I have two different test tubes, and you should be able to look at these and determine which test tube contains liquids that are miscible, meaning they're mixing in all proportions, and which test tube contains liquids that are immiscible, meaning they are not mixing in all proportions. So if we look at the test tube on the left, notice that these two substances are completely mixed together. I don't see any separation. It is completely uniform. This represents two substances which are miscible. That means that the two substances in this test tube have to either both be polar or both be nonpolar. Let's compare it to the test tube on the right. Notice this line of separation here. This means that these two substances are not mixing in all proportion. We have one substance here on the bottom of the test tube, and we have a second substance floating on the top. This is a clear separation. They are not mixing in all proportions. This represents two substances that are immiscible. That means one of them must be polar and the other one must be nonpolar. So let's look at a few examples. And in order to do this, we need to remember overall polarity rules from first semester. Determine if the following are miscible in water or hexane. So I'm going to draw some quick Lewis structures. Alright, so one liquid is going to be water, the other one is going to be hexane. And we want to know if the following are going to be miscible in either water or hexane, and it's going to depend on its polarity. So first one, let's do methanol. B, carbon tetrachloride. For this unit, you will not have to draw Lewis structures again. You've already been assessed on those. I will give you the Lewis structures. You do need to do polarity though. And the last one, let's do acetone. All right, so the way that we want to approach this problem is polarity. We need to look at overall polarity. So water, is it polar or nonpolar? You should have water memorized by now. We use it all the time. Water is going to be polar. Again, the way that we want to determine overall polarity has to do with the difference in electronegativity values and our vectors. So oxygen is going to be more electronegative. It's going to have a greater pull on those electrons. And then these two vectors are going to add, creating an overall dipole pointing up. Hexane is a hydrocarbon. Notice that it's only made up of hydrogens and carbons. Hydrocarbons are always nonpolar. So now let's do the same thing with A, B, and C. We want to base it on my central atom, which is this carbon, and we want to determine, is this polar or nonpolar? Because of this oxygen, methanol is going to be polar. Those vectors are not all going to cancel. Carbon tetrachloride. Note that my vectors are equal but opposite, so they cancel. Equal but opposite, so they cancel. Carbon tetrachloride is nonpolar. Carbon to carbon, carbon to carbon, but here I have this carbon to oxygen. This is also going to be a polar molecule. All right, so now after all of that work, we can finally answer the question. A, B, and C, are they miscible in either water or hexane? Well, like dissolves like. Methanol is polar. It is going to be miscible in a polar substance. Methanol would be miscible in water. Like dissolves like. Carbon tetrachloride is nonpolar. It's going to be miscible in a nonpolar substance. So it would be miscible in hexane. Last one, acetone is polar, like dissolves like. It would be miscible in a polar substance like water. So the last thing that I want to talk about is how ionic, polar, and nonpolar compounds differ in water. So we're going to draw an ionic compound, a polar compound and a nonpolar compound. In water. Alright, so let's start with ionic. Let's say this is my beaker. And I'm going to have some water molecules. So here's my water. Oxygen gets the partial negative. Those hydrogens get the positive. So let's say I had an ionic compound like sodium chloride. Sodium is positively charged, it's a cation. Chlorine is negatively charged. So what you should know about ionic compounds is that they dissolve in water, but not only do they dissolve in water, they dissociate, which means they're going to break up. When sodium chloride dissolves in water, you are not going to see any sodium chloride molecules. Instead, what you're going to see are sodium ions and chloride ions. So the main thing that we need to know for an ionic compound is not only does it dissolve, but it also dissociates. This sodium chloride molecule is going to break up. That positively charged sodium will be attracted to the partial negative oxygen of water. The negatively charged chloride ion will be attracted to that partial positive hydrogen, and that is going to cause sodium chloride to separate or dissociate. So ionic compounds dissolve and dissociate. Next, let's look at something that is polar. So again, I'm still going to have some water molecules, H2O. And water is polar. And then let's say I had this is my carbon, hydrogen, 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 and then it's attached to a chlorine. So this would be CH3Cl. That chlorine makes this a polar molecule. So what we're going to see is that this molecule is going to mix in all proportions. We are going to see that it is going to be completely dispersed throughout our beaker. Meaning that it is dissolving. So a polar molecule in water dissolves, But notice that I did not separate any of those atoms. It dissolves, but it does not dissociate. So notice the difference between these two beakers. In the first one, sodium chloride broke up. In the second one, my molecule did not break up. Polar compounds do not dissociate. Ionic compounds break up into individual ions. Polar molecules are not made up of ions. They are not going to dissociate. Last one. Let's look at something that is nonpolar. What that would look like is your two substances will not mix. You would have a clear separation. And it'll depend on the density of which one is on the bottom and which one floats on the top. But notice now the difference between polar and nonpolar. If it's polar, the molecules are completely mixing together. If it's nonpolar, they are not mixing together. We would have a clear separation.